let's talk a little bit about magnets and magnetic fields. And right over here, we have a picture of what today we would call a magnet, where we have these metal nails all being attracted to the stone. And the stone, the modern name for it is magnetite. And human beings have known about magnetite for thousands of years. In fact, the name comes from ancient Greece. There was the Magnetes people who settled actually two areas that are often talked about in the origin of the name magnet, which are referred to as Magnesia. And depending on the historical count you see, it was one of those Magnesias where the ancient Greeks were able to find a lot of what we would call magnetite. And actually the element magnesium, which is not related to magnetite, was also found in that area, which is where it got its name. But it wasn't just some interesting thing that would attract metal. And they also obviously observed other properties, that if you had two pieces of magnetized magnetite, it actually turns out that not all magnetite is magnetized. Something interesting has to happen to it. We believe it's actually lightning strikes that magnetize it naturally. That the orientation matters. If you're in one orientation, they might attract each other. And then if you're in another orientation, if you were to spin this one around, they might actually repel each other. And this notion of the orientation, that there might be some polarity, made it more than just an interesting thing to observe. In ancient Han China, roughly 2,000 years ago, they invented the first compass, where they realized that if you took some magnetized magnetite, which the historical name for it is a lodestone, and you allow it to freely move, and you could do that by either hanging it from a string or have it float on some still water, say in a bucket, that it will consistently orient itself so that it points in the same direction. And so you can use that for things like navigation, which the Chinese did roughly 1,000 years ago. And that helped us realize that the Earth itself is acting as a magnet. And just like a small magnet has different sides to it, the Earth does too. And that's where the convention for a north and south pole of a magnet came from. But there's probably a question in your mind from the first time that you noticed a magnet. If you have some piece of metal out here that's not touching the magnet, and in a future video we can even talk what touching even means at a microscopic level, but if you have a nail out here that's not touching it, but there's some force that's acting at a distance on that nail, how does that nail know to be pulled towards that magnet? It doesn't have eyes, it doesn't have ears, it doesn't say, oh, there's a magnet there, I better somehow move myself towards it. There's something about that region of space that is interacting with that nail. Or if you think about two magnets, how does it know the orientation of the other magnet to either be attracted to it or repel it? How does it even know that other magnet is there? And that's where the concept of a magnetic field is useful. And this was introduced by Michael Faraday in the 19th century as a way of at least thinking about, giving us a framework for this force at a distance. It doesn't exactly tell us what it is, but it gives us a way of predicting and thinking about what is happening. And one way to visualize a magnetic field is to take a bar magnet, or I could even say a bar lodestone, and put it underneath a piece of paper, and then put metal filings on top of that piece of paper, and you will see something like this. In fact, I encourage you to do this, to observe this yourself. And you see what look like lines that are essentially connecting the north and south poles like that. And this notion of field lines, we can draw it a little bit clearer in something like this, was introduced by Michael Faraday. And he says, okay, there's this thing called a field that tells us for every point in space around the magnet what it would do to something that is interacting with the magnet, another magnet or maybe a piece of metal. So for example, if you were to put a small bar magnet right over here, the north side is going to be repelled from the north side of this bigger bar magnet, and the south side is going to be attracted to it. And so what you could do is you could put a freely moving magnet, or you could put a compass to actually see what the orientation is. Which direction will a compass point? And it will point in the direction of these field lines. And if you were to put it over here, it would orient this way if you allow it to freely move, where this is the northern end and this is the southern end. And if you were to put it here and you were allowed to freely move, let's say as part of a compass, and if this is the northern end and this is the southern end, it would orient like that. And so that helps you draw the field lines and also know the direction. And just by convention, the direction is we're coming from the North Pole into the South Pole. And what Faraday said is, not only does this tell you the direction of the magnetic field, it tells you the magnitude based on the density of these field lines. So for example, the magnetic field is stronger here, where in that unit area that I just made, you have very dense field lines, while it would be weaker right over here. I have fewer field lines. Now, another amazing thing about magnets and their polarity that people have noticed since ancient times is you would think, at least initially, that if this has a North Pole and a South Pole, then maybe you could separate these two things. Maybe if you were to break this in half, then you could have a pure North Pole magnet and you could have a pure South Pole magnet. But that's not what happens. When you break this in half, instead you have two magnets, each with their own north and south poles. And then you can keep doing this. And early scientists just kept doing it and said there might not be any limit to how much you can cut this. Obviously, when you keep cutting and cannot cut any more while retaining the properties of the magnetite, you're getting down to now the molecular level. And in future videos, we'll think about how even at a molecular level, you can still have a little tiny magnet that has a polarity to it. Now, another really interesting thing about magnets is this connection between magnetism and electricity. People have also observed that if you took a current-carrying wire, and the current is going from the positive to the negative end, so it is going in this direction, and if you make it go through a piece of paper that has metal filings, it looks like field lines are forming here. Magnetic field lines. And it turns out it does interact with the types of things that tend to interact. It will interact with magnets. And so this is a magnetic field that is being formed by an electrical current. And so that was the major clue that the phenomena of electricity and magnetism are in fact related. And this relationship is what allows us to do things like have electric motors or generate electricity from wind or water turbines. And it's out of the scope of this video, but I'll give you a little bit of a clue of how these things are connected. We know that things are made up of atoms, which are made up of particles like electrons and protons, which are charged. And we know that a current, an electric current, is based on the movement of charged particles. That when something is not magnetic, say a non-magnetic piece of magnetite, all of those charges are moving more chaotically. But if something happens to it, maybe a lightning strike, it can align how they move so that they act in concert to have a more coherent magnetic field. So I'll leave you there. I'm already getting a little bit ahead of our skis, so to speak. But I do think it's really interesting to appreciate how all of these puzzle pieces that we see in nature fit together.